In the following videos, we are going to discuss transmission line theory. Typically, when working with a circuit, we aim to connect the signal source to the load to allow the load to receive the signal. This connection involves using a wire to transport the signal. Using classical circuit theory, we can determine the voltage on the load ZL by applying the voltage divider rule when connecting a signal source with a source impedance ZS to ZL. It's important to know that the transmission line we'll be discussing here is not a simple wire. In fact, it's a line that has a precise definition in electromagnetism. This type of line consists of a live wire, a ground, and it is uniform throughout the structure. There are several types of transmission lines commonly used. For instance, a two-wire line features two conductors, one for the live wire and the other for the ground. An example of this is the cable that was used to connect old days TVs to an antenna, as which you can see in the diagram on the right. Another example of a transmission line is the coaxial cable commonly used in cable TV systems. It features a conductor in the middle and a metal foil wrapped around the outer shell as a ground. This structure also consists of a live wire and ground. The less widely used type is signal routing on a printed circuit board (PCB). If a signal line is placed above a ground plane, it's called a microstrip line. However, in theory, an ideal microstrip line has an infinitely large ground plane. In any case, the structure of these lines remains uniform throughout. If we were to cut the line at any position, the cross-section would have exactly the same structure. You might be wondering why we need to learn about transmission line theory. Well, as the signal frequency increases, its wavelength decreases. When the signal wavelength shortens to the point where it's no longer much larger than the circuit dimension, a transmission line effect can occur. That's why it's essential to understand the transmission line theory. So why does the transmission line effect occur? It occurs due to a standing wave on the line. This effect can cause the load impedance we expect to be, for example, 100 ohm, to be converted to 300 ohm or 500 ohm, or even a complex value impedance at a certain operating frequency. As a result, the circuit may not meet the original design requirements. This effect is directly related to frequencies. The higher the signal frequency, or the longer the line, the more apparent the transmission line effect becomes. There is another important reason why we learn this theory. As circuit designers, dealing with electric and magnetic fields all day long can be challenging. Therefore, we want to translate the viewpoint of electric and magnetic fields into circuit problems. Once we can translate electromagnetic effects into a circuit perspective, we can use voltages and currents to consider these effects in our circuit designs, which has many benefits. In this diagram, the left side represents the lower operating frequency and the right side represents the higher operating frequency. The right side represents the shorter wavelength and the left side represents the longer wavelength. It illustrates the theory we can use when dealing with different signal frequencies or wavelength. When the frequency is lower and the wavelength is longer, we can mostly use classical circuit theory to deal with the problem. When the frequency increases to 10 MHz, 100 MHz, or even 1 GHz, and 10 GHz or tens of gigahertz, there's a great chance that we will need to use the microwave theory. Once the transmission line effect occurs in the circuit, the results from classical circuit theory may be incorrect. Now, you might be wondering, is microwave theory different from classical circuit theory? The answer is no, not really. We can think of microwave theory as a modification of classical circuit theory at high frequencies. As the frequency goes higher and we enter the realm of light, we use optical theory to solve the problem. You might find it strange that we use microwave theory to deal with signals at lower frequencies, such as 1 MHz or 2 MHz, which frequency seems not so high. However, the answer is that it depends. As we mentioned earlier, when the signal frequency is higher or the wavelength is shorter relative to the line, the transmission line effect will be relatively apparent. The telegrapher's equations or transmission line equations were developed to deal with problems such as submarine cables laid under the ocean. These cables could be tens or even hundreds of kilometers long, and although the frequency of the transmitted signal may only be in the order of kilohertz or megahertz, the transmission line effect still occurs. That's because the signal wavelength is short compared to the cable of tens of kilometers, which is a relative problem. In the next few videos, we'll talk about transmission line theory.